So one of these things is not like the others. We know that a relativistic theory shouldn't have time so prominent in it. And if we have a look at the Schrödinger equation for a scalar particle in one dimension, one spatial dimension, then we can see we have this very strong difference between what's going on in terms of space and what's going on in terms of time. In other words, we have second order derivatives in terms of space and first order derivatives in terms of time. And so we know that that's basically not relativistically correct. And indeed, this comes from the kinetic energy p squared on 2m, which is very clearly non-relativistic, and then a potential. Okay, so what is the relativistic version of this? So we want a scalar particle in one dimension. How are we going to do that? Well, we've got two options. The first thing is we can get rid of the second derivative in space and just have all single derivatives, or we could go to second order in time as well. So we've got this phi, and we want to have some kind of scalar equation that says something equals something. Really, if we try and take just a single derivative of that, then we've got a dangling index. What are we going to do with this mu? We've got to close it with something. And so indeed, our first guess might be to have two indices like that. So this is the Dalenburg operator again, and that's a scalar, so it might work in an equation. And you'll note that what we've got is second order derivatives in space and time. So we've gone that route. And so how are we going to get the rest of it? Well, this is a bit like our energy is equal to p squared on 2m plus v. And so what we've really got here is a kind of IH bar time derivative going for our E, and we've got a minus IH bar spatial derivative being our momentum. And so what we're thinking about really is replacing that with the relativistic version of the same equation. And so then we'd have something like, we'd apply this to phi on both sides. This term here, if we take it over there, we're just getting something like that, up to a factor of h bar squared. And so in fact, our guess for this equation, dividing both sides by c squared, is that. And that is known as the Klein-Gordon equation, which interestingly was in fact discovered by Schrödinger. When he was trying to derive the wave mechanics for waves in quantum mechanics, i.e. his original Schrödinger equation, he actually started here because he knew about relativity at the time. And as we discovered, there are very few options for generating a wave equation. This is a wave equation for a particle with no potential. This is just a free particle of mass m. And we really didn't have a lot of choices. We could have terms that were scalar like that, and we could have terms of that. We could have had terms with higher derivatives. We could have had, for example, quadruple derivatives, but that's not physically motivated, and obviously it's more complicated. So this really is the kind of equation you get stuck with if you're going to obey relativity and feel you have some right to make a wave equation for a scalar field. Let's have a look at what kind of solutions the Klein-Gordon equation has. It's fairly easy to show that just like the normal Schrödinger equation, it has plane wave solutions. So at first glance that's quite reassuring because this is the same functional form of wave solutions for the non-relativistic Schrödinger equation as well, except that the energy now has the correct special relativistic relationship between energy and momentum. So it sounds like we've done very good things. Except that we do have a rather strange thing in which this energy here can go to minus infinity. And it's a fairly strange physical universe where you can get a higher and higher momentum and slide down and down in energy. So you can always access more energy just by going faster. And so as you can imagine, in that kind of situation, the waves behave very strangely and non-intuitively. And indeed, you can't just cross out the negative energy solutions, even though they might be unphysical, because they're needed to make a complete basis. Without those solutions to this equation, you do not have the ability to say what happens to an arbitrary initial state. So that problem seems to be strongly coupled to the idea that we have these second order derivatives. So when you've got the second order derivative in time, you end up with quadratic equations which have kind of plus and minus solutions. At a deeper level, actually, this is our first hint that relativity is constraining quantum mechanics in very deep ways. It's telling us that there's something kind of wrong with writing down a wave equation for a scalar particle. Indeed, the Klein-Gordon equation doesn't describe a real scalar particle. There's an equation very much like that in field theory, where the objects here are not scalar fields for a particle, but in fact field operators. But we can't go into that now, but just to give you an idea that relativity is already telling us that there are structures that we can and can't have in quantum mechanics. If we try and describe a scalar particle with the Klein-Gordon equation, then bad things happen. For example, in non-relativistic quantum mechanics, you can define a density. The density is just given by the mod squared of the wave function. And indeed, in terms of dynamics, you can talk about a current. So a probability current is given by, and the reason that's the probability current is that these two things have a continuity equation, that the rate of change of this probability density is given by the div of the current in the normal way. So this is just conservation of mass, and you can see why that then is the current. Relativistically, we combine these two things into a 4 vector. And indeed, the Klein-Gordon equation shows that we have a continuity equation for this. Remember, for 4 vectors, continuity equations look like this. However, the components of this, the density that you get out of this, does not stay positive. So the density out of this is that, and unlike the normal Schrodinger equation, which gives us a density that is guaranteed positive, this one is not. These derivatives can be defined more or less independently of the field, and so I can construct a negative density there. And if I evolve this equation, I can start off with a situation where I have positive density and evolve to a situation where I have negative density.